Hello. We are going to look more carefully at the proof of asymptotic normality, and I set up this big picture in the previous video. So we would like to calculate the limiting distribution of this estimation error with this adjustment, square root n adjustment to prevent this guy from converging to zero. And then to do this, we start from the first order condition. The estimator is obtained by maximizing the estimated criterion function. So it always satisfies the first order condition as long as the criterion function is continuous, like differentiable. And then from this something equals to zero equation, this part can be linearized, can be converted into a linear function of this, which because we need this, so we intentionally we would like to have this term using the Taylor expansion and multiplying square root n and subtracting a and dividing by b, we obtain this result. So to show this limiting distribution, we need to show this converges to the normal distribution. And it requires two separate convergences. First, we are going to show that square root n times a n converges to a normal distribution. So square root n times a n will converge to a normal distribution by the central limit theorem. And then the other bn inverse will be converging to a constant, actually a constant matrix. It must be a matrix. So then, and once you obtain this and this two convergences, we can combine those two convergences by the Slotsky theorem. So Slotsky theorem requires one to converge to a constant, and so we need to show this. Right, yeah, it is. So I hope like this is the most difficult proof in our course. So I hope I had a blackboard, but and I find that reading the lecture note is not effective. So I made a presentation slide, and then now what we are going to do here is we are going to look at each step, like this step, Taylor expansion, and this, and we will study what kind of assumptions we need to fill the gap. So I will provide the assumptions, and I will explain why we have those results. Okay, next, Taylor expansion. So if you look at the Taylor expansion statement, so it's a simplest version of Taylor expansion, because in general you may expand up to higher polynomials, but we only use the first order. So this is the statement of the Taylor expansion. So for some, there is an intermediate value theta bar n. I intentionally put n here because theta bar changes when theta hat changes. So theta bar is always in between theta 0 and theta hat. And when theta hat changes, theta bar will change. So I use n to show its dependence on theta hat. And like for any n, always theta bar is in between theta hat and theta 0. And if you replace the function g with this derivative of criterion function, which is what we are going to use in our Taylor expansion, and then it is easy to see that an, the an and bn can be found this way. So an is the first order difference, and bn is the second order difference. But the difference here is second order derivative, by the way. I said difference. So an depends on theta 0. So it is fixed, so it does not cause a big problem. But bn has 2n. So the criterion function may change if you increase the sample size. If you have different data, then your estimated criterion function will be different. And at the same time, theta hat will be theta bar can be different. If you have different data, then theta hat will be different, and then theta bar will be different. So Bn is a composite sequence. When n increases to the infinity, this part changes and this part changes too. Two parts change at the same time. So later we are going to study how to analyze this. And I told you how to handle this kind of composite sequence. And the assumption in this process, in this step, the assumption we need is differentiability. So the Taylor expansion requires differentiation of G. So if G is differentiable everywhere, then we are good. And in this case, G is the first derivative. So it means the criterion function must be twice differentiable. So already it's the first order derivative is differentiable, means the original function must be twice differentiable, right? This is a mild assumption. Then next, let's study B first. And we are going to show that this Bn sequence converges to something constant, H. H is something, and H usually stands for Hessian matrix, because the criterion function is differentiated twice. So anyhow, and as I said, the problem here is that it is a composite sequence. There are two sequences. The first sequence is a sequence of functions, and the second sequence is a sequence of vectors, parameters. And the parameter is easy to handle. We know you can show that the parameter, the intermediate value, converges to the true parameter if the estimator is consistent. We learned how to prove consistency, and if you have the consistency result, then the intermediate value also is consistent. So I use it as an assumption. So this is already assumed. If you assume consistency, you have consistency of the intermediate value. So it's okay, it's good. And second thing here is the second derivative can be written in this way. So think it as a log likelihood function. So the second derivative of the criterion function is the sample average of the second derivative of log likelihood function. So if you imagine this is the MLE estimator, L can be interpreted as a log likelihood function, but right? Then the second derivative is a sample average of something, second derivative function, and what we need here is this sequence. So there is one sequence and another sample average. So there are two so both as theta converges to something and the sample average will converge to something, they must converge to something together. It's typo. We need this. This is what we need. So theta hat and the sample average must converge at the same time. So theta bar converges to theta 0, and sample average converges to population average, population mean. This is the idea of uniform convergence. Uniform convergence is required, and as I discussed earlier, the sufficient conditions for the uniform low-large number, this kind of uniform low-large number, is compactness of the parameter space and continuity of this function and stochastic boundedness. So the expectation of supremum must be finite. So under these three assumptions, we can show we have this result. Therefore, then it is clear H is this guy. This is not random because it is a population mean. There is no randomness in this part. So L second derivative and I means L is a function of random variables. And once you show this, after showing that, after we have shown that Bn, the sequence Bn converges in probability to H. The Hessian matrix H, it's another typo. Same typo is repeated. As you can see. Okay, fixed. So after you show that the sequence converges to a Hessian matrix, then now we would like to show its inverse converges to the inverse of the limit, like this. And we need, the only assumption we need is the limit must be non-singular. Then we found, we got an answer to this. So this part is cleared. So, and in the next step, we need to show this part. And remember, for each step, we need different assumptions. So we are going to combine all these assumptions together to have the whole asymptotic normality result. Okay, I'm going to continue in the next one. So see you.